Assalamualaikum warahmatullahi wabarakatuh. For our group project, we introduce the voltage response in a simple RC circuit. So we choose electrical engineering application of calculus. We focuses only on capacitor voltage response in an RC charging circuit, and all resistance values are below 20 kilo ohms to match the GeoGebra slider limitation. We have exponential function, differentiation, tangent, and rate of change. So this is our group members. We have Sarah. The entry number is CN 230158, and we have Akmal Shukri CN 250036. We have Said Akbar AN 250004, and me Muhammad Haris P. Amiruddin is AN 250084. Okay, now let's look at the problem background. In a real engineering application, RC circuits may seem simple, but they are used in many electronic systems such as timers, filters, delay circuits, and signal smoothing circuit. One important characteristic is that the capacitor voltage cannot change instantly when a DC voltage is applied. Instead, it increases gradually over time. The speed of this change is determined by time constant represented by TRC, where R is the resistance and C is the capacitance. This behavior is very important because the capacitor voltage determines when a circuit reaches a certain threshold, activates the next stage, or smooths out unwanted fluctuation in a signal. So the main engineering equation is how does the capacitor voltage VT change over time, and how fast does it charge? Understanding the response helps engineers choose suitable resistor and capacitor values to achieve the desired circuit performance.
Now we focus to mathematical model. For our group, we choose the formula is a V bracket T is refer to capacitor voltage equal Vs, and a Vs is refer to DC source voltage bracket 1 minus equivalent power of negative T is time over RC. For R is referred to resistance in ohms, always below 20 kilo ohm, and capacitance in farad. And the equal Vs bracket 1 minus equivalent power of negative T over time constant. The time constant is equal RC. For the key means, a large time constant produce a slower voltage rise.
Now that the mathematical equation has been introduced, I will explain the structure of this model and simulation of this model. And after that, the calculus and the different results obtained from this model. And as in this slide, as we can see, they explain the structure of this model. So, in this whole structure is made with 4 slides, which we can move manually, depends on our need. So, the first one is resistant, which is represented with by RK, and with the values from 1 to 19.9 kilo ohm. The second one is capacitance represented by Cu with the value from 0 or 1 to 470 microfarads. The third one is supplied voltage with the value from 0 or we can say 1 to 24 volts. And the last and the fourth last and fourth one is A, which allows us to select a particular moment during charging process. Now, as you can see, the formula and GeoGebra, which is VA is equal to Vs multiplied with 1 minus e to the power of minus a divided by t. So, here, The T is this is a constant time, which is equal to RC, R multiplied resistance multiplied with capacitor. Mathematical analysis. This slides actually presents the calculus behind our model. As we already explained in the GeoGebra simulation video, that the derivative represents the instantaneous charging rate of the capacitor, which we got from capacitor voltage equation. As we can see in the graph, the charging rate is highest at the beginning and then gradually decreases as the capacitor approaches the supply voltage. Results in this slide are these slides have gathered the results that we demonstrated and the simulation video, GeoGebra simulation video. So as we can see here down here and the left down here, after 0 to 1 second, the capacitor reaches to 63.2%. As we can see down there, 63.2% of its final voltage. And after 2 seconds, that was 1 second, as we can see there, after 2 seconds, it reaches to 86.5%. And just like that, after 5 seconds, we go on to the 5 seconds for this. So after the 5 seconds, it reaches to approximately 99.3%. 3%. So these are the values that has been demonstrated for the default one, which I already did in the simulation. I showed everything in the simulation video, explained everything there. So we also observe in this slide, we also observe that increasing the resistance or capacitance increases the time constants and slows the charging process, while the final voltage remains equal to the supply voltage. And that's it from my side. Now my other friend, my group member, will explain the last part, conclusion, and this is our project for the mathematics.
Okay, in conclusion of this project, the RC voltage response provide a practical engineering example of how calculus can be applied in electrical engineering. The charging behavior of the capacitor follows the exponential function described by the equation V of t equals V source multiplied by 1 minus e to the power of negative t divided by RC. The time constant t equals RC determines how quickly the capacitor charges and provides a useful design parameter in real circuits. The derivative of the voltage equation represents the instantaneous charging rate and is closely related to the tangent law of the charging curve. And using GeoGebra, it allows the mathematical model to be visualized clearly and interactively, making the engineering interpretation easier to understand. And finally, it should be noted that this model is ideal in real circuit component tolerance, leakage currents, equivalent series resistance, and temperature effect can cause deviation from the theoretical response.
I just had to let you know you're